What is the bottom one?
So that's the way they always have it.
No, the VGA should not. There is no good adapter to output to a Mac. It would never work. Usually, it doesn't work. So it's for the Mac. It's always have to be a mini DisplayPort or a straight output HDMI. If you try to do VGA on the Mac, it's not gonna work.
Okay.
The PC might work.
I was gonna say so PC was probably working.
Yeah.
PC.
Yeah.
Okay. Thank you, Narcissus.
No problem. But are you able to capture your thing? So
yep, it's here. It's
okay,
streaming.
okay, good. Okay. So I was worried that you needed to VGA to get your capture, but you didn't need that. All you need to do
no, it is
this
VGA.
to work.
You went DisplayPort to VGA.
Okay,
yeah.
But if it was HDMI, you wouldn't be able to get it. Is that correct?
No, I would. Either way.
Either way, it's good here. Okay.
Yeah. Thank you.
You got it.
Oh, I'll bring that adapter back.
this work, and I wanted to ask, how do we find new 2D materials, and how do we find materials that are also 2D and magnetic? So this is leading to this data-driven study of these 2D materials. How do we take what we know about graphene, or MOS2, black phosphorus, CGT, or chromium triiodide, and learn which one of these materials, without doing complicated calculations or measurements, are stable, conducting, ferromagnetic, non-magnetic, and so on. Okay. So we'll do this data-driven study, or materials informatics study, and it has two main purposes: to do materials discovery, that is, in particular to learn what 2D materials might exist that are also magnetic and chemically stable, and to learn some new physics, to do knowledge discovery. What about the properties of these collection of materials will develop new insights into our understanding. And in particular, we'll focus on ferromagnetic 2D materials. Okay, so skip the gun. Now we've talked about what is materials informatics, but I haven't really explained it. You know, a picture is worth 1,000 words. It's kind of like teaching computers material science using machine learning. Now this is just a joke, but there's no laughter. No, really, it's the combination of machine learning and material science, where the goal is to predict the magnetic moment. And this is typically something that's either hard to measure or hard to calculate, using inputs that are easy to pick up or easily attainable, such as atomic properties, including number of spin-up electrons, number of valence electrons, and so on, where this function, f of x, is approximated using machine learning. This is a new way of studying 2D magnetic materials. So why do we want to use machine learning anyway? Why not do a lot of experiments and a lot of calculations? Well, there's a lot of materials out there. There are a lot of potential materials out there. For instance, the ICSD, the Inorganic Crystal Structure Database, has over 180,000 entries. The Chemical Abstract Service has over 49 million organic and inorganic molecule entries. So the search space is quite large. So doing serial calculations can be quite challenging, and doing serial experiments are going to be slow and expensive. Okay, so I've talked about so far what is materials informatics. Now I'll discuss the when and the where and the who of materials informatics, and I'll use a clever analogy. So imagine that you are Plato, and you're in ancient Greece, and you like to learn more about what a small set of random elements, how they behave. And these are your elements. You have iron, magnesium, air, fire, water, earth, and you have some things about their properties. You know their color, and you know their atomic number. Okay, because you're a Plato, you're clever, you ask yourself, what is a good descriptor to describe these data? What are the trends in these data? And again, because you're Plato, you're clever, you choose the atomic number as your descriptor, and you want to apply a model to these data. That's to arrange them in the increasing order of the atomic number. And once you do that, you get the following. You have hydrogen, helium, lithium, air, fire, water, earth, beryllium, and so on. You notice there's a trend in these data, that the atomic number increases by number 1. And if you pick up this as a rule, you'll kind of realize that there's something wrong with this entry right here. Perhaps there's an error in the understanding or error in the data collection. And there's something else that's interesting. There's no 7. It goes from 6 to 8. So I'll ask you, if there are any chemists in the audience or perhaps extremely talented physicists, what is supposed to be here? No, extremely talented physicists. Don't be shy. Nitrogen, yes, it's nitrogen goes right here. So because you're clever and you can play this game, you go looking for nitrogen, and you continue this process, and you end up with the periodic table of elements. But we're not talking about chemistry so much. We want to ask, can we apply this idea to crystal structures, to inorganic crystal structures? This is a crystal structure for diamond. This is a picture of a diamond that has these nitrogen vacancy centers. And that is when you take a carbon atom and place it with nitrogen, and the neighboring site is empty or vacant, so it's nitrogen vacancy center. And it so happens that when you have NV centers, diamond will have a nice red color. So the question is, can you learn some structure-property relationship here that tells you, given a particular structure, what is a property or color? Can we map structure of the diamond lattice to a color? Perhaps more intriguingly, if we take two hexagonal lattices, we decorate one hexagonal lattice with carbon atoms, and the next hexagonal lattice with boron and nitrogen. We might ask, how do their properties differ? How can we go from something that's conducting to something that's insulating just by changing the decoration of the lattice? And can we extend this to some other structure that has a hexagonal lattice decorated in some way? Can we predict the properties of that structure without doing complicated calculations or expensive experiments? So we've talked a little about the materials we're interested in, and the next step is to kind of talk about the tool that we'll use to study these materials, and that's machine learning. So let's dive into what machine learning is and why it's useful and why it's become more popular in the past few years, maybe the past 5 years or so. And that's because we now have lots of data, lots of descriptors, and easy access to statistical models. There's really now the rise of the materials databases that didn't exist, say, 10 years ago. And people are working on developing these chemical space descriptors, these mathematical descriptions of molecules and crystal structures. Examples that are kind of old now, but comprise the Coulomb kernel and the bag of bonds representation. And there are also nice data science tools that exist, but you don't have to code yourself. For instance, the scikit-learn and Google's TensorFlow. So more on the data. Everyone knows that data is in a cloud. It's a tough audience. So there's Materials Project. That is a DFT database. There's also AFlow, which is another DFT database. There's MatNavi, which is hosted by NIMS, the National Institute for Material Science, based in Japan. I actually worked here for a few months. And there's OQMD, the Open Quantum Materials Database, and NOMAD, the Novel Materials Database. This is also a repository of DFT data, and the Inorganic Crystal Structure Database, which comprises experimentally obtained crystal structures. And you can access these and mine data to do fun, exciting discoveries. There are also descriptors. These are, again, mathematical descriptions of molecules and inorganic crystal structures. There are a few approaches to picking up or obtaining descriptors. There's what I like to call the kitchen sink method, where you get all the descriptors available to you and you put them together and you try to figure out which one is useful for making the prediction you're interested in making. There's also the domain knowledge approach, where you stop and you think very carefully about what you want to predict and you derive descriptors that are appropriate for that task. You can use a combination of these two approaches in your work. An example, in addition to the one we saw a bit earlier, is imagine you're doing work on ionic compounds. We know that they have different columns in the periodic table. So a good descriptor could be, for instance, the column number of the periodic table. Now, for statistical models, we all are familiar with linear regression or linear regression models, where you fit a line to some data And you may not be familiar with this classification model, or models based on decision trees. And I'll explain a little bit what this means. So this is for classifying whether someone should get a credit card or not. And these are the descriptors: age, if the person is a student or not, what the credit card rating is. And so you can ask, what is the person's age? If they're young, you ask, are they a student? If they're not a student, you don't give them the credit card. If they are, you give them a credit card. And you can also apply this to doing regression. And there are tools that really fit everything together. You have your database tools, such as PyMongo. You have tools to transform your data using Python. You also have tools to model your data, such as Pandas and scikit-learn, and tools that you can, once you have your nice results, visualize and show it to your friends and your family, show you've done a really nice job. This is really easily available to physicists. So it's really easily accessible, and you don't have to spend a lot of time coding things yourself. Okay, so switching gears again. So the main topic of this talk is 2D magnetic materials, and I'll focus now on exactly which magnetic materials I'm interested in studying. This is of the class of the transitional metal trichalcogenides, or the ABX3 crystal structures, where the lattice is shown here on the left. And from a top-down view, you can see it right here. An example I've talked about before is chromium germanium telluride, which is expected to be a ferromagnet down to the monolayer. And so chromium sites sit on these A sites. The germanium atoms sit on the B sites. The tellurium atoms sit on the X sites, 3 above the plane and 3 below the plane. And if you look here, the chromium atoms form this hexagonal lattice, which is decorated by germanium and tellurium atoms. And so what happens if you look at a material that has a very similar structure, but is now chromium silicon telluride, you'd find that the magnetic order goes from ferromagnet to anti-ferromagnet, which is, for me, quite intriguing. So to emphasize that, you start with chromium germanium telluride, and it's ferromagnetic, and that means all the spins are aligned. And you consider different magnetic configurations, such as this Neal anti-ferromagnetic type, where each opposite site, each neighboring site has a spin anti-aligned. And you can consider this zigzag anti-ferromagnetic constructor, where along the zigzag edge, the spins are pointing in one direction, and along the other direction, they're pointing in a different direction. Turns out that chromium silicon telluride is this zigzag anti-ferromagnetic type. But for the purposes of this study, we'll focus on the ferromagnetic configuration and this Neal anti-ferromagnetic configuration. So let me emphasize this again. You start with some structure, chromium germanium telluride. You swap germanium for silicon. It's not a magnetic atom, but you change the magnetic order quite a bit. So the idea was how far can we play this game of changing the atomic substitutions and studying what happens to the magnetic order. So that's what we did. We created about 200 ABX3 structures using density functional theory calculations. If you kind of play around with substitutions ad nauseum, you get about 10 to the 4 different possibilities. And we calculated the ferromagnetic configuration, anti-ferromagnetic configuration, and also the non-magnetic case. And we extracted the formation energy, the magnetic order, and also the magnetic moment. In particular, we substituted one of the 2 atoms in the unit cell for another transition metal, keeping one fixed, that's chromium. These are examples of the substitutions in the first row of the transition metals, and also the second row. The B sites are combinations of silicon, germanium, and phosphorus. For instance, you can have silicon 2, or silicon germanium, or germanium phosphorus. And the X sites are either tellurium, selenium, or sulfur. This is a view graph showing you where the atomic substitutions live on the periodic table. These are the transition metal substitutions. These are the B site substitutions, and these are the X site substitutions. Oh, that's a great question. And so when I first started this, I wanted to keep my data set relatively small. And so I thought, well, I have to include chromium and neighboring atoms. And I also want to include magnetic atoms like iron and cobalt. And I wanted to go down to copper, so I included nickel as well. And I didn't want to, I just somehow missed this. And well, I thought I wanted to include ruthenium because there's ruthenium trichloride, which is kind of interesting. And I meant to include molybdenum, but I forgot. And I picked up some other two. And it turns out we have other calculations later on, but we started with this set. That's a great question. So we'll address stability as well. And they're certainly not all stable. For instance, copper is not going to be stable. And depending on how you arrange these atoms, you may have something that's stable, or could be stable, but certainly not, or definitely not stable, one of those two. Any other questions? Okay. Great, so once we have all these structures, and we can calculate some things by picking a subset of 200 structures, we can now display the results. Now what I'll display here is the difference between the ferromagnetic configuration, the difference in energy between the ferromagnetic configuration and the anti-ferromagnetic configuration. And that's shown here, where these panels are X equals thurium, selenium, and sulfur. The vertical axis is the transitional metal substitution. The horizontal axis is the B-site substitution. The color represents the difference in the energy. So if it's blue, if it's if it's red, if it's a negative number, if it's red, if it's a positive number, then you expect these structures to be anti-ferromagnetic. But if it's blue and a negative number, you expect it to be ferromagnetic. For instance, chromium, germanium, telluride, shown right here, it's blue, and so it's ferromagnetic. You might notice that there's some colors that are in like a magenta and also black, which is not quite dark blue. And these are structures which have their initial configuration flipped to the other one, so we can't constrain this delta E. One important thing I forgot to mention, if you look carefully, you can kind of pick up some patterns in these data. For instance, the regions that have this anti-ferromagnetic regions, and the regions that have almost degenerate configurations. And there's some that are also kind of clustered around ferromagnetic configurations. And our hope is to train a statistical model to learn these patterns and exploit them quantitatively. So we can do something similar for the magnetic moment as well. Data are shown here, where again we have X equals thurium, selenium, and sulfur. And again, the horizontal axis are the B-site substitutions, and the vertical axis are the transitional metal substitutions. The color is now the magnetic moment, and a dark purple is showing a large magnetic moment. And if you look at the panel, you find that there are clusters of large magnetic moment which change in their texture as you go from tellurium to selenium to sulfur. And there is some interesting pattern as you go up to group 6 of the periodic table. And our hope is to train a statistical model to learn this pattern and exploit it quantitatively. So let's go back to the magnetic excitation. Now, before I explain this to you as a tool of getting which structure was either ferromagnetic or anti-ferromagnetic, but we can also pick up something interesting, such as the value of this delta E, or what is the magnetic excitation energy. And we can use this value as a kind of like energy gap to estimate something like the Curie temperature. So if we do that, we can start with the Heisenberg model, which we can use to write down the energy of these different states in terms of the exchange coupling. These J's, or parameters that parameterize the exchange coupling of your interactions with different sites. And you can use this expression, which is an analytical expression that couples your J to the Curie temperature. And if you go through this analysis for select structures in the data, you get the following, or this is formula, magnetic moment, this magnetic excitation energy, and this is the Curie temperature. This is the value for chromium, germanium, telluride, about 40 Kelvin, which happens to be what it is in experiments. It could be an accident because these values are really just estimates. So the absolute value isn't so important. What's really important, though, is the relative value of this Curie temperature. And we find that there are some structures, such as chromium phosphorus telluride, which have much larger excitation energy and much larger Curie temperature. So if we were to try to synthesize these, we might expect that the Curie temperature for this structure has a much higher value than that of chromium germanium telluride. Okay, so far I've talked a lot about the magnetic properties, magnetic moment, magnetic order, the magnetic excitation energy. But now, once we have a structure that has some nice magnetic properties, we want to ideally make it and have it not fall apart in the lab. So we are also concerned with chemical stability, and we'll use formation energy as a proxy for chemical stability. And if we do that, we get the following for X equals tellurium, selenium, sulfur. Again, traditional metal substitutions, B-site substitutions, where the color now is the formation energy. And the darker you get, the more negative formation energy you have. And so that means more chemically stable you are. The lower the energy you have, more chemically stable you are. And there are trends here you can pick up pretty readily as you go from the left to right on the periodic table. You find that these structures are becoming more and more chemically unstable, or less having lower or higher and higher formation energy, or more positive formation energy. But as you go from the second row, from left to right, it kind of resets and you have a similar trend going from more to less chemically stable. And going from tellurium up the periodic table to selenium and sulfur, the trend is generally that you get more and more stable structures. Question?
The program tell you the crystal structure?
The crystal structure here is fixed, is ABX3 type. Actually, that's a very important element.
Oh, it's always stable.
There's some that are not so stable.
They're not positive. But more importantly, have you constrained these to two layers? Or three-dimensional?
Oh, I forgot to mention, they're all one layer. They're all monolayer structures. That's right.
So by definition, that's defining the outer.
Defining the atoms?
It's defining what atoms at the surface.
Finding what atoms at the surface. I'm not following.
Well, there are two surfaces.
Mm-hmm.
These are centrosymmetric structures as well as structures. That means you define what the outer atoms are. Never
That's right. We start with a crystal structure, and we basically we define what the atoms are going to be in that particular structure, and they calculate their properties. Any other questions? Okay. Great. So we have all these nice data, and ultimately we want to be able to exploit the machine learning tools to understand these data. So the next few slides, I'll explain how we do that. So our machine learning models require some inputs, and we need to develop some mathematical description of our structures, and these are known as the materials descriptors. There should be something that's kind of easily attainable, and I'll use the atomic properties for this study. And we use the atomic properties to construct a property of a structure or a compound. And I'm taking something simple like the mean of these properties or the variance of these properties. If you do this, you get a total of about 61 possible descriptors. Examples of atomic properties include the number of spin-up electrons and the atomic radius. We can kind of check to see if this is really a sensible thing to do by doing some nice visualization. So if you make a pair plot of formation energy, variance of the dipole polarizability, variance of the ionization energy, and the average number of valence electrons, you get the following. If you just focus on this top row here, I'm plotting formation energy versus dipole polarizability, ionization energy, and number of valence electrons here. We find that there's an interesting trend. So there's a highly there's a high correlation between formation energy and the dipole polarizability, the variance of that value, and a correlation between the formation energy and the ionization energy. And so right away you can imagine making a simple linear fit to estimate what the formation energy could be given this really simple descriptor. So we'll do something a little bit more complicated other than a linear model, and it's going to be called something called a random forest, and it's based on this thing called a decision tree. I'll explain a little bit more about what that means. So our model is a random forest model. We take inputs like the number of spin-up electrons. The output is going to be something like the magnetic moment. We take training data and test data. I'll explain a little bit more in a few slides exactly what that is. And we basically minimize the loss function of this model to estimate what the model should be, a good model should be. So what does this mean? I find the best way to explain this is to show some pictures. So this is a sine curve. So the underlying behavior or function here is a sine function, and I've added some noise. This is just a toy data, not linked to my actual experiment. So I have data here and some target here. And this is the first node of this decision tree. So it estimates everything to the left of this point in this region to be this value, everything to the right of this region to be this value. If I make my tree depth a bit deeper, I go to level 2, the fit becomes a little bit better, and to level 3, it starts really approximating this sine curve, and it's not getting bothered by the noise in the data. But if you go to too low a level, if your function becomes too complicated, you start fitting to the noise. This is bad. So you play tricks on avoiding fitting to the noise, but while still learning underlying behavior of the data. This is what we did. We used a random forest model, and we trained it on some data, and we tested it on data, and there's this training testing sequence, which I'll explain here, in perhaps something that's more familiar, doing a linear regression. So everyone here is fitted the line mx plus c to some data in the past. So you have data that's taking some x and has some value y. And let's say these data were taken over the course of 6 months. It took you 1 month to measure or calculate each point. In the end, you have something that looks like a line, but you want to continue getting some more data. So you say, what should I do? I'll make a nice linear fit to these data. And if I have additional test data, these red squares are test data, I don't actually have to measure them. I just have to look at my linear fit, and I can look at the x value of the thing I want to get at to figure out what the y should be. It's a bit crooked, or the x value of this one, figure out what the y value should be. So actually, it's pretty spot on in this example, and so on. So the machine learning in this particular example, it comes down to picking values for the coefficient, m and c, the slope and the intercept. Okay, so if we apply this random forest regression to our data for the magnetic moment, we get the following result. And here I'm not showing you a linear fit. I'm showing you the calculated magnetic moment from the DFT. Machine learning predicted magnetic moment on the y-axis. This dashed line now is just a guide to the eye. So if all the data were falling exactly on this line, you would have a perfect prediction. But if you look at it, you find that the predictions for the training data, these green circles, and the test data, the red squares, are not so bad. One of the nice things about this random forest model that you can use it to extract feature importances. By doing an analysis on a random forest, you can say the number of spin-up electrons, the average of that value, is the most important descriptor in making my fit work well. The next most important descriptor is this thing I call CS-Bob, the chemical space bag of bonds descriptor, which I can explain to you in some detail later if you like. Other important descriptors include number of valence electrons, the dipole polarizability, and the variance of the number of spin-up electrons. Question? So I guess you're asking to explain how we get these feature importances? Yeah. So you have some, you say you have 10 descriptors, and you take one out, and then you do the regression, and you see how worse, how much worse your result is becoming. You put it back, you take another one out, and you kind of do this, and you find which one is giving you the without it has the worst result, or the result is decreasing the most, and you can rank it in this kind of way. That's how they do it. Any other questions? Yeah.
Have you found these open source efficient enough to provide robust latency description that they can bring down properties versus having their
That's a great question. I'm glad you asked it. So in the beginning, I told you there are all these really great databases that exist, but I did my own DOT calculations. And that's the answer to this is linked to your question. And so I wanted to predict something, magnetism, something that's fairly complicated. I didn't emphasize enough that you're learning this emergent phenomenon, and it's something that's a little bit challenging to learn. And the data that exists have different crystal structures. And so the one that I showed, there's this graphene, which is this hexagonal, and there are different combinations, and they're not necessarily only hexagonal lattices, and some are magnetic, some are not. And there's really a challenge to learn, as you say, the latent descriptor. What is a good thing to pick up to map your structure to the property? That's a tough question. That's actually still an open area of research. And so what I did is I constrained someone else brought this up. I constrained my data to only have one structure, so I wouldn't have this problem. So I have a pretty simple-minded set of descriptors, which work fairly well, but they wouldn't work if I were to look at a different crystal structure, for instance. So it's a challenging problem, and one has to think carefully about how what you can get from your data and what tricks you can play to extract knowledge from it. Does that answer your question? You're welcome. Okay, so we're here and we've managed to learn some descriptors, and this is really a tool for knowledge discovery. Perhaps there was a descriptor here which doesn't make sense. You mentioned the number of spin-up electrons is something that's kind of reasonable, but perhaps there's something else that didn't quite fit with what we understood about magnetism, and it showed up as one of our important descriptors. We would take pause and think about why is this an important descriptor, and perhaps learn some new physics. Okay, so we can also do something fun, which is to classify whether something is ferromagnetic or not. The results are shown here. And we can do this using a random forest, but actually this model known as support vector machines performs better. And I can explain a little bit later if you like what a support vector machine is. But the result is, for predicting ferromagnetic structures, we have about 82% success. And for predicting anti-ferromagnetic structures, we have about 80% success. This is a confusion matrix where this is the truth on the vertical axis. This is the prediction on the horizontal axis. And an example is, so if you predicted something that's ferromagnetic, 42 plus 9 times, but only 42 of those times it's actually ferromagnetic. 9 times it's actually anti-ferromagnetic, so you have this 82% success rate. This is full DFT in this case.
So
yeah.
it may not prove.
That's right. That's right. Yeah. So I'm comparing everything to DFT data right now.
But that's like how you.
Yes, that's a great question. It'll link. Think about Professor Mundy's question at the very end of the talk. It'll come back. It'll come back to serve us well. Okay. So we can do this classification. It's pretty exciting. This success rate is not bad, I think, for the data size that we used. And the next step is to perhaps not do any machine learning, but just look at the data that we have, see if we can learn some physics. So we'll plot the crystal structure versus the magnetic moment. So this is a crystal structure. We could look at distances like A1, A2 distance, the A1, X1 distance, so adjacency pairs and their distances, and map that to the magnetic moment and see what we find. So we take our 200 structures and we plot this A1, X1 distance versus magnetic moment. We get this pattern. it tends to suggest that at some distance of a1, x1, we tend to have larger magnetic moments, and others tend to have smaller magnetic moments. If we plot the x1, x2 distance, this guy here, against magnetic moment, we find that at some distances, magnetic moment tends to be larger. So we say, there must be some link to the distance or the structure of this lattice and the magnetic moment. We could do more kind of robust analysis using principal component analysis, where we plot the magnetic moment versus the first principal component, and the magnetic moment versus the first and second principal component, where the color here is the magnetic moment, and we find that it clusters in the center of the graph. Now, if you don't know what principal component analysis is, I have a slide for you right here. So you have some descriptors, x1 and x2, and in principal component analysis, you find a new basis that explains most of the variance in your data. So the first principal component is along here, because most of the variance is happening along this axis, and the perpendicular axis is going to explain the next amount of variance. You can do this also in 3 dimensions and a much higher dimensional space, and it's a tool to do dimensionality reduction and also kind of pick up, if all your inputs are interatomic distances, you do analysis like this and you make a plot, you get a sense of, well, it seems to be that there's a link between structure and magnetic moment. Okay, so we've done a lot of machine learning of magnetic properties, but we haven't done anything with formation energy. And we like to take some structure, some candidate structure, and predict its formation energy as well. So let's do that next. So the results are shown here with the DFT calculated formation energy on the x-axis and the machine learning predicted formation energy on the y-axis. And they have results using different machine learning models. There's kernel ridge regression, which is like a linear regression model with constraints. There's the random forest regression, which I've explained to you before. And this is a model based on neural networks, which I can explain to you later if you like. And we find that so this dashed line is the guide to the eye in all the plots. We find that our point or training data and our test data are falling pretty close to this line, which means that our model is performing really, really well for predicting the formation energy. So this is very promising. So what we can do, we have models that can predict the formation energy and models that can also predict the magnetic moment. So what do? We make predictions on structures we haven't trained a model on. If you do that, we find a magnetic moment over here on conditional metal substitutions we haven't seen before or DFT data hasn't been calculated on. They're shown here. We can also calculate or predict using machine learning the formation energy of, and this set is 570 structures. And from a total of, well, let me say we've predicted over 4,000 structures, and I'm showing you only 570 in this figure. To highlight this, the regions here which you can find have large magnetic moment, here and here, and it jives with what we kind of expect from the chemistry intuition. And the regions of these graphs where you can expect to have a very unstable compounds and a few that should perhaps be chemically stable. Next question?
The difference between that?
This is magnetic moment
Okay.
and formation energy. And I've only plotted tellurium for the magnetic moment for some technical reasons. It turns out it works well for tellurium, but not for selenium and sulfur. We can talk about that later if you have questions on that. Any other questions? Okay. So let me start again. So we've been able to train a model with only 200 structures, but have predictions for 4,000 structures. So this took me a few months to calculate by DFT. This might take a couple of years, and I don't want to do that. So what I can do is use machine learning as a crutch to explore a very large space of materials without actually doing the calculations. So the idea is you have some DFT data, you create a small data set of structures, you train a machine learning model with these data, you make a prediction of a large data set, but you don't necessarily trust all your machine learning predictions, they have uncertainties. So what you do is you select perhaps the ones that are most favorable, and then you do a confirmation by the DFT. And so in the end, you have a slightly bigger DFT data set, which you can then feed into a machine learning model again, screen it, what happens is your model gets better with more data, and you can repeat this cycle. So in the end, you want to use this framework for doing screening, find one or two structures that are really desirable. So you start with a large set of data. You screen for ones that are chemically stable. You screen for ones that have a large magnetic moment, if you're interested in ferromagnetic structures. And if you do that, you can have particular search criteria, larger than 5 Bohr magnetons or less than about 1 EV. And you find that there are certain candidate structures which we could potentially make and measure. Question?
I mean, you started out with this thing that has a hexagon shape and it has little teeth and a solid bottom. For a simple model, say that is kind of stable as is the hexagon. Right structure.
Yeah.
Get it full.
Yeah, I haven't thought about that. There are a certain set of structures that certainly exist in nature and fit this structure type. The choices that I'm making, I haven't assumed that they will fit the structure type. Certainly will be the case that some of them won't, and you can't make all of them in the lab. So the goal is to try to find, is just to screen away those structures that definitely won't be chemically stable. Yeah. So now this gets to the next slide, I think, is answering your point really well. So we have these results from DFT and machine learning, which were verified by TFT, but we've only done DFT so far. So in the end, oh, by the way, if you want to read some more details, please visit my preprint on the archive. So we have these machine learning models. We have made some predictions. What do we do from here? Well, we need to have some synthesis and verification using experiments and measurements. And there's Joe Cikelski, he's part of the CQUIM, which I'm discussing with, and hopefully we can work together to get this done. And there's also, further into the future, maybe a few months or some years, to not just look at 2D magnetic materials that are based on chromium germanium telluride, but expand that into things like oxides, where really exciting physics can emerge. And for this, I'm hoping to get some collaboration with Professor Julia Mundy to combine synthesis and materials informatics approaches to find new exciting materials with interesting properties. So to summarize, we've identified new chemically stable 2D ferromagnetic materials. We've shown that we can tune their magnetic properties and chemical stability by making atomic substitutions. We've used machine learning to make fast estimates of over 4,000 ABX3 type structures. We picked up their magnetic moment and their chemical stability. And this is a new framework for probing magnetism in 2D materials. I'd like to acknowledge CIQM for their support over the years and these computational resources, Exceed and Odyssey. I'd also like to thank everyone in the Kixigris group, especially Daniel Larson, who's here, and Marius Mathiakis, who's maybe in the audience. And I also like to thank Joe Cikelski, Jenny Coulter, Pavlos Protopapas, Sada Shankar, and Vinny Manoharan for very, very useful discussions. Thank you.
Talk about after we've already got our
Yeah, that's right. That's absolutely right. Once we have a candidate structure, we want to really explore that.